Uh, Tell us about randomized versus deterministic decision tree size.
Thanks. Thanks everyone for coming, and thanks for having me here. It's a pleasure. So today I'll be talking about joint work with Arkadev, Yogesh, Jaykumar, Swagato, all of whom are at various different institutes in India, spread pretty much all around India. I'm the odd one out here. So throughout this talk, I'm going to be talking about Boolean functions and decision trees. Please feel free to interrupt me at any point. So the objects of interest in this talk are going to be Boolean functions that take n bits in input, output 1 bit. And unlike some of the previous talks, we only care about total Boolean functions. So we want our functions to be defined on the whole Boolean cube. Now, very quickly, let me tell you what decision trees are. So a decision tree is a model of computation of Boolean functions. So a decision tree is a binary tree where internal nodes are labeled by variables. You have edges labeled by values in 0 or 1. And then you have leaves labeled by values either in 0 or 1. So this is an example of a decision tree that computes a 4-bit function in the natural way. So on input x, what this decision tree does, it first checks the value of x1. If it's 0, go down the left subtree. If it's 1, go down the right subtree, and then recurs until you hit a leaf. At this point, output the value seen at the leaf. Okay. So this is a decision tree T, and it very naturally computes a Boolean function f that's defined by x reaches a 1 leaf. That is a leaf with the label 1. Okay. And now we care about several models of complexity of decision trees. So one motivation for studying decision trees is a nice way of capturing what a query algorithm does. So this exactly captures a query algorithm for f in the following sense. First, an algorithm queries the value x1, then depending on whether the value is 0 or 1, you make the next query as dictated by the tree and so on. And the query complexity of the corresponding algorithm is the worst case number of bits seen, which is nothing but the depth of the tree. What we're going to care about, as the title gives away, is the size of such trees. And this is a very nice abstraction from your usual model of computation, where you actually care about what the computations are in between these queries. But the query complexity is abstracts that completely out, which is why it's somewhat nicer and easier to analyze and has more structural properties and such. Okay, good. So let me throw out a bit of notation that I'm going to be using. So I'm going to use the notation. So for a tree T, I'm going to use the notation Qt of x to denote the set of variables so on input x, if you run the decision tree T, what is the set of variables queried? I'm just denoting using Qt of x to denote this. So we have the natural measure of query complexity or decision tree complexity, which I'm going to denote by D. So D of f is the minimum depth of a decision tree that computes. Now we can talk about some generalizations of decision trees, and the generalizations that we care about are going to be those where an algorithm is allowed to query more general functions than simply the variables of the input. So one particular example is where an algorithm is allowed to query ORs of arbitrary subsets of the input. So this I'm going to denote by D OR of F, or decision tree. And what is an OR decision tree is just like, instead of nodes being labeled by variables, you allow nodes to be labeled by subsets of the inputs. And then, so an example where a very simple example where an OR decision tree is gives considerably more power than regular decision trees is for the OR function. You can show that D of the OR function is n, but D OR of the OR function is just 1. Okay. I'm going to look at D OR, D and, sorry, the same definition with OR replaced by and. Also going to look at D and comma OR. And in the and comma OR model, we allow algorithms to query either ands of subsets of inputs or ORs. So both, I mean both. Yeah. Okay. And another model that, of course, it's evident from the title that we care about, is the size of a decision tree. And what's the size? Let's just say the number of leaves. And this up to a factor of 2 maybe is equal to the number of internal nodes, but we don't care about constants. So let me say D size of F. Instead of minimum depth, we have minimum number of leaves of a decision tree that computes F. Okay. Good. So here's the first proposition that sort of motivates, in some sense, why we should look at size or why we should look at and or trees. So in some sense, in this query world, the depth of an algorithm is, in some sense, a proxy of time complexity in this query setting. And I want you to think of and or query complexity or size complexity as an analog of space complexity in the query complexity world. Okay? It's not quite true, but it makes some sense, I guess. So here's the first proposition, which is folklore, I guess. All Boolean functions F Okay. One more thing is, whenever I'm using the notation theta tilde, I'm abusing notation a little bit. Theta tilde always hides factors that are polylogarithmic in the input size. So polylog n factors. So let's look at a proof for this, at least. One more thing I should mention is that this D OR of F, the OR query complexity of F, the OR query model, corresponds to this setting of combinatorial group testing that people look at, where you're allowed to query ORs, arbitrary ORs of subsets of the input. Okay. So if you want to show that, so let's start with the other direction because it's easier perhaps. So given and or decision tree, what you can do is you can just simply expand out all ands and ors by just regular variables. So for example, if you have a node that queries and you want, let's say you have T0 and T1, this you can simply map to so let's say S is x1, x2, x3 for now. Sorry, 1, 2, 3. So this is an expansion of a single node that had an AND query into one that has just variable queries. And as you can see, the size doesn't blow up too much. Like there's a factor of potentially n that the size blows up by. So in general, if you started with a depth D tree here, what you're going to end up with is a size n to the D tree or so, roughly. So that shows this direction. And for the other direction, so I'm going to hand wave a lot of stuff. Just feel free to stop me whenever again. For the other direction, we can use this. There's this tree balancing or protocol balancing argument that you may have seen in other settings. Let's start with a regular decision tree T of size S. Now you can argue that there is a subtree that contains a fraction of vertices or nodes that's somewhere between, that's a fraction between 1/3 and 2/3 of the original size. So what you can do efficiently with an AND OR query algorithm is you can use one AND query and one OR query to determine whether your input reaches this node. If it does, then you've cut down on at least 1/3 fraction of the remaining nodes. So you've lost a factor of 1/3 in the size. And if it doesn't, you're again in this subtree, which again, you've lost at least a factor of 1/3 in the size. So you do this log many times. And so from a size S decision tree, you get a depth log S and OR decision tree. Good. So this is next, what we're going to look at, again, as the title gives away, is randomized measures of decision trees. Again, very quickly. So randomized, the view that we're going to take for decision trees, randomized decision trees in this talk, is that a randomized decision tree is a distribution over deterministic decision trees. And what will require for correctness is that so we're going to say that a randomized decision tree T mu, so this is a distribution over decision trees where the distribution is denoted by mu. So we're going to say T mu computes F if for all inputs, the probability of it making an error is small. Okay. So you randomly sample a tree according to T mu, run it on X, the probability of making error is small. And what are the complexity measures of a randomized tree? It's just the worst case complexity of a deterministic tree in the support. Okay. So R of F is the randomized analog of perfect. It just came here. R of F is it's a minimum over all randomized trees that computes computing F maximum over all T in the support of mu D of F, D of T, sorry. So yeah, I mean, minimum depth of a decision tree is just D of T. So yeah, so this is the randomized query complexity or randomized decision tree complexity of F. Similarly, I'm not just going to write down everything else, but you just put the word randomized in front of or query complexity and query complexity or randomized size as well. Okay. Other questions at this point about definitions? These are essential to get. Yeah.
So for AND or tree, can we assume that it's balanced up to constant factors or something? Like the optimal AND or tree for any problem?
Good question. I'm pretty sure we can. Yeah. I'm pretty sure you can. I'll get back to you after. Yeah, I'm pretty sure an argument like this will be able to balance. Okay, very good. Now let me tell you about one result that's relevant to our paper. Actually, I'll start it here. So it's a result from Nisan in the early 90s. So basically what Nisan showed is that in this query complexity setting, randomness doesn't provide a super polynomial advantage. Phrased differently, this says that in the query world, P is equal to BPP. I hope that excites some of you. And at this point, so this is in some sense a de-randomization of depth. And I'm just going to state our main theorems. So there's a log cube n factor in here that's hiding inside this O tilde. I'll get back to log factors in the end of the talk, but for now, let's say we don't care about them at all. Okay. So in some sense, this answers the space analog of whether de-randomization is possible in the query world or not. And it is up to log factors, which we can also get rid of later. Spoiler. So first thing is, this answers an open question that we had posed in an earlier work. We had essentially asked this question in a different language. And interestingly, our motivation was from a complete different perspective. We had posed this with the hope to get more efficient quantum query algorithms. So that was a paper about quantum query complexity. And using similar techniques as to what we use to prove this, which I'm going to prove to you soon, we are also able to answer. So I should put in a corollary here. For all f total Boolean functions. So deterministic and or query complexity is at most a fourth power in randomized and or query complexity of 2 log factors. Just by this proposition. So that's our first result. And our first result, a second result, sorry, we use similar techniques as we do here, slightly more effort maybe. Again, for all f Boolean functions, total Boolean functions, you get so even the and query complexity of f is randomness doesn't provide a super polynomial advantage, discounting log factors, which again I'll get back to later. And we using the same, essentially the same idea, we can prove the same result for all decision trees as well. And yeah, this So Knopp, Lovett, Maguire, and Yuan had asked essentially this question in 2021, whether and decision trees can be de-randomized. And we answered that in the positive. Okay. Just as a side note, before I dive into the proof, I just want to say here, there's a result of, I'm not going to write down all the authors because it's going to take me some time, but I'll say it out. It's Ambinis, Balodis, Belovs, Lee, Santha, and Smotrovs in 2017. They showed, and I'll write down the initials, A, B, D, L, S, S. So it's not known what the true polynomial separation is here. For all we know, it might be true for all Boolean functions. Deterministic is at most quadratic in randomized. For all we know, there exists a function that witnesses a cubic separation. And this is, there's a lot of research going on in this area. I'm sure maybe 10, 20% of the audience here have thought about this problem at some point. Any questions at this point?
So the corollary is only for depth, not size.
Yes, sorry, I should have mentioned this. Good point. So except for this measure here, the size, all other measures are depth measures. Yeah. So and decision trees, or decision trees, and or decision trees, all depth. Yes.
Another notion of size, this DAG size.
Sure. Yeah. They're typically harder to analyze, I guess. Yeah, I don't know what happens with respect to DAG size. I'm not sure. Maybe proof complexities might have a better idea of what happens. It's my guess. Next question. Okay, if there's no more questions, I'm going to sketch very quickly how Nisan's proof was, and then how we attempt to adapt it to prove our main theorem. So in my opinion, at least, I mean, the key technique used in Nisan's proof is his definition of this combinatorial quantity called block sensitivity. Which I'll define. And then what Nisan went on to show via some other combinatorial measures as well, intermediate combinatorial measures, showed that small b less. So this, just combining these two gives you Nisan's result over there. So I'm going to define block sensitivity of a function f at an input x. So this is n0 to the n. Number is trying. This is a bit of a mouthful. So let me just illustrate with an example. So block sensitivity is just counting the number of possible sets such that if you flip the values of your input x completely on these sets individually, then the value of the function changes. So, and I'll just give you an example in a second. So let's look at the OR function on n variables. So this outputs 1 if and only if there's at least one in the input. Okay. And let's look at the input that's 0 to the n. I'm just going to write it out 0, 0, 0. And now I'm going to claim that every singleton here is a sensitive block. So in other words, define Si is equal to I. So all of these SIs are disjoint from each other because they're singletons. And moreover, because the function is the OR function, the property is that if you flip any of these blocks around, so if I change this 0 to a 1, the function value changes. And of course, you can't have more than n sensitive blocks because there are n elements in your whole universe to begin with. So block sensitivity of a function is at most n, and block sensitivity of OR is n, as witnessed by the input 0 to the n. Okay. And in some sense, this inequality here is the way the proof goes is you fix a certain number of variables such that f becomes an OR on BSF many variables. And then you can analyze just from first principles that the randomized query complexity or randomized decision tree complexity of OR is omega number of variables. Question? Okay. Now we're going to attempt to prove theorem 1 here by adapting Nisan's proof. And my attempt my initial attempt is going to be very silly. I'm going to replace d of f by log d size of f. And does anyone see a problem with this? So for the OR function, we have block sensitivity to be n, but its decision tree size is very small. Like log decision tree size is just log n. Why is this? So the OR function has a simple decision tree. 0 on the left, I guess. So this is size n or n plus 1 or something. So in some sense, this fact that block sensitivity captures the hardness of OR sitting inside it is a weakness for us, because we really need a function that has large size that's sitting inside it. And what we do to get around that is we define this analog of block sensitivity, which is a counting analog, which we're going to call block number. So this fails. Which is the maximum number of minimal sensitive blocks of f at x. So in the OR function, if I'm looking for minimal blocks, there's only n of them because all of the singletons are minimal, right?
What is the maximum? Maximum of what?
Sorry, you're right. I just mean number of minimal sensitive blocks. Yeah. So for example, if I look at the majority function, let's just take an example maybe. and I look at the all 0 input, you can check that the block sensitivity of this is basically like 2 or 1, depending on how you define block sensitivity. But you have several minimal blocks here, like any size, any subset of size n by 2 or n by 2 plus 1, depending on your definition, is a minimal sensitive block. And this is, I guess, our idea of why this is maybe a more right measure if you want to analyze size. Several minimal sensitive blocks. In some sense, the intuition is that if you have trees computing f, each of these blocks correspond to a path. That's a very high level idea. So shortly after we defined this, we realized that this has actually been defined earlier. And the earliest we could trace it was to a work of Kulkarni and Tal in 2016 or 17. And this was defined in a similar context, but not quite the same, where they were looking at fractional versions of block sensitivity and certificate complexity and other combinatorial measures. Perfect. And now I will finally get down to what our key structural results are, and hopefully prove at least one of them. With the title of the workshop. And this is going to be, in some sense, where did Nisan's proof go? Yes. In some sense, this is going to be an analog of, let's call this 1 and let's call this 2. I'm going to write something that I haven't defined yet. I'm going to define it soon. So log NF is a quantity that deterministic decision tree size can be upper bounded by the square of this quantity. I'll define it in a second. So this first bullet point I want you to view as an analog of Nisan's first inequality, and the second bullet point is exactly putting this intuition that I had phrased in words into a formal statement. Log randomized size is at least log block sensitivity. Up to everything is polylog factors. Let's ignore that for now. Let me define n of f maybe. So what's an F monochromatic subcube? It's just a subcube of your original Boolean cube, and a fine subcube, where F takes a constant value. And N of F is, like, in some sense, N0 of F, which I'm not splitting up this definition, but this is in some sense the non-deterministic complexity of F. Non-deterministic, very complex. And it's not very hard to show that if you have an efficient cover of F by subcubes, then you can actually get small size decision trees. If you've seen it before, this just follows from like D is at most 0 certificate complexity times 1 certificate complexity. Just that argument, if you write it out, you get log D size with the order of log square n of F. So if I put this in over here, I substitute n of F, and then I substitute log block number by log R size. This, I hope I haven't written things wrong, but this should imply this. So what I'm going to do is I'm going to leave some space, come back to the proof of this in the end, maybe. I'm hoping I'll have time to prove at least one of these. Hopefully both, in fact. Now, these are our key structural results that we use to prove theorem 1. And for theorem 2, we use another key intermediate measure, which is not block number, but which is 0 fractional hitting set complexity. Which, unfortunately, I don't think I'm going to define it here. I'm happy to talk about it offline. This is a measure that has been looked at in the past. For example, this paper of, or the precursor paper to this of Shahar and others, they looked at this quantity. So what we show here is, again, this is a quantity that I haven't defined yet. F. So in other words, this first statement is somehow a strengthening of this fact that I said that D is at most C0 times C1. You can actually make this stronger and argue that this complexity, which I will define now, is also upper bounded in terms of this cover number. And I haven't told you what the 0 decision tree complexity of F is. So in 0 decision trees, you allow arbitrary variables to be queried. But the depth of a leaf, you only count the number of 0 answers that are there. So for example, if you look at the AND function, the 0 decision tree complexity of it is just going to be 1, because on any leaf, you're reading at most 1 0 in the trivial tree computing it. And it turns out that up to log factors, up to polylog factors, D up to a log factor, D0 of F is essentially the same as the AND decision tree complexity of F. And R0 of F is essentially the same as the randomized AND decision tree complexity of F. So we get AND of F. This is up to log factors. 0 of F. Sorry, 0 superscript. By 1. It's not hard to show that R0 of F is at most log randomized size of F. Sorry, my mistake here. Log n of F. The other way. To show this, we need the fact that cover number is at most, log cover number is at most log square randomized size of F. And that follows from our statements here. Just plug in this plus this exactly gives this equality here. Log n of F is at most log square R size of F up to log factors. And R0 of F, it's given a small zero decision tree, it's easy to come up with a small size decision tree. And I mentioned earlier that zero depth complexity is essentially and good. So now what I'm going to do is maybe I will just verbally give you ideas as to how we prove these. And then if you're interested, I can formally prove it offline. Okay. So to show this, what we're going to do is we're going to start with a small size randomized decision tree for F. And what I need to do to you is I need to exhibit a cover of your input space, a F monochromatic cover of it. So what we'll do is first look at fix an input X. And suppose its minimal sensitive blocks are W1 through WK. So this is a hand wavy proof of 1. Now, the first property we need is that given a randomized decision tree computing F, the probability that on input X, that you're going to see a variable in W1, let's say, this probability is at least 1/3. So in other words, what am I saying? So let T be a randomized DT for F. So for all X, so I've fixed an X, sorry, let's work with this X. So the probability over the randomness of the tree that on input X, you have queried a variable from W1 is at least 1/3. Okay, maybe I can leave this here for a second. Why is this true? Because if you haven't seen a single variable from W1, then your randomized tree hasn't distinguished between X and X with W1 flipped. Right? And by definition of sensitive blocks, these have different values. So what we can do now is we can repeat T several times. What is several? It's log block number. And then we expect that for every X, we've hit all of its blocks. I'm not going to formalize this now. I can formalize it later. And the next property that we're going to need is that if on input X, you have queried a set S such that S intersection Wi is non-empty for all I, So suppose on input X, you've queried variables in S, and suppose it so happens that S hits this collection W1 to WK. Then we're going to need to conclude that S is a certificate for X, for F at X. What does this mean? This means no matter what input you have, as long as it's consistent with values in S that you've read, its function value is the same as f of X. So in other words, all inputs consistent with this is F monochromatic. So what we're going to argue in here is we say if you repeat T in the sense that if you sample from this randomized decision tree log block number many times, what's going to happen is that for all X, you're going to see certificates for them. And now each of these certificates are going to correspond to F monochromatic subcubes. But a certificate is since we've repeated the tree only log block number many of times, there are only a small number of possibilities of transcripts that you've read. That's the idea. And the number of transcripts that you've read is exactly this, log block number times log R size, or R size to the block number. And after taking logs, you get this is a very high level sketch of it. And a very high level sketch of 2 as well. Why not? So let's fix again X, and let's fix B, which is a sensitive, minimal sensitive block of it. So this means f of X is not equal to f of X plus B, where f of X plus B is just X with the values in B flipped. So I'm going to call this input X sub B for convenience. Yeah. So now in the input X sub B, I'm claiming that if you look at X sub B, if you flip the values of B, then all singletons in B are sensitive for X sub B. Why is this? Because otherwise you would have, if any of these are not sensitive, then you would have been able to delete that from B and you would have a smaller sensitive block for X. So now again, using the same property that we see here, on the input X sub B, if you have a randomized decision tree computing F, on input X sub B, with probability at least 1/3, you're going to read I. And this is true for all I in B. So in order to show 2, what we can do is repeat your original randomized tree poly n many times. And what's going to happen is for many sensitive blocks of X, you'll argue that on those inputs corresponding to those sensitive blocks, on those X sub B's, you've read this whole set B, in fact. And then what's going to happen is that each of these, you can argue, go to a different leaf. Yeah. So if you have several sensitive blocks for an input X, half of them are going to correspond to inputs that lead us to unique leaves in the randomized tree. This is the very high level idea. And this is formalizable, in fact, in a few lines, which I don't have time to write down. Other questions at this point? Now, what I'm going to do is I'm going to spend a couple of minutes addressing log factors. I know people don't really care about log factors, but sometimes it's important to care about them. And someone has to. delete theorem 1. Okay, no worries. So let me write down it's nice because now I can actually put down the log factors. So this is our theorem 1 if you work out all the log factors. And what I'm going to claim is that for all f, totality is very important, and totality has been important throughout. I know I've been hiding it everywhere, but if you ask these analogous questions for partial functions, they're immediately known to be false. Like there are exponential separations in whatever measures you care about, or we cared about here at least. So I'm going to claim this with a, again, hand wavy proof for now. But if we have this, then I can replace this by each of the log n's, I can replace by log r size. So log deterministic decision tree size is truly polynomially related to log randomized decision tree size.
That's big O or omega?
Big O, this one.
The bottom one, log n.
No, this is omega. This is. So this log n, I'm upper bounding by log r size.
I guess you're assuming f depends on all the inputs.
That's true. So f is a total function. Okay, yeah. Okay, I need f depending on all inputs. You're correct. Otherwise, I'm sure there should be a simple hack to get around that though.
Reduce n.
Sorry?
Reduce n.
That gives n.
No, reduce n. No.
You want the same
Reduce n, sure. Yeah, I mean, yeah, I guess throughout, let's maybe from the beginning of this talk, let me go back and jump and say f depends on one. Sure. Yeah, otherwise, n doesn't make sense. Right. And why is this true? Just say a couple of words about it. So towards a contradiction, suppose randomized size is at most n by 10 or something. So this means that the randomized query complexity is at most n by 10. Right? It actually means that the non-adaptive randomized query complexity is at most n by 10 or so. And this we can show to be not true fairly easily because f depends on all inputs. So this is a high-level sketch of how we would show this. Okay. So in theorem 1, we have no log factors. In theorem 2, this was relating and query complexity or query complex, deterministic and randomized. Here we actually need a log n. So if you look at this function, that's the threshold 2 function on n inputs. So in other words, this outputs 1 if there are at least 2 ones in your input and output 0 otherwise. So it's not very hard to show that any deterministic tree, even with and or queries, has to have omega log n depth. But on the other hand, if you even just allow and queries, perhaps I may need or here maybe. Fairly simple construction where you just sample a subset of the inputs, query its or, query the or of the remaining inputs, check whether they're both 1. That's the idea. Repeat this a few times. And this gives you a constant cost randomized or protocol. So this shows that you really need a log n here. So that's the log factors. Some more things I wanted to talk about. So what are the best possible separations that we can have? So here we have a, okay, now let's go back to ignoring log factors. So here we had a power 4 separation between log deterministic size and log randomized size. Here we have a power 3 separation between OR query complexity and randomized OR query complexity. The first thing I want to say is that D versus R separation lifts to D and or versus R and or D and versus R and separation. What do I mean? I mean, if you have a function f witnessing d of f is omega rf to the k, then you can come up with another function f prime that witnesses this measure of f prime is omega r this measure of f prime. And this was first pointed out to us by Weiqiang Yuan. We thank him for that. And here's a simple argument for constructing such an f prime is just replace f by f composed with XOR on 2 input bits. So each of your n inputs, just replace it by an XOR on 2 input bits. So you now have a function on 2 n inputs. And it turns out that log D slash R, maybe for now, size of f of XOR is essentially the same as D slash R of f. So the depth of f somehow corresponds to log size of f of XOR. You can show this. And the same thing holds true for D and of f of XOR as well. Which in some sense makes sense, right? I mean, an XOR gadget is obfuscating the inputs. You need to read all pairs in some sense. Corresponding to one query in F, you have a blow up in f of XOR. Okay. So what this means, so this just implies that any separation carries over. Another thing I want to mention is that up to log factors, our result number 2, just from these observations here, will recover Nisan's D at most R cube, which also I seem to have erased. I had everything important on this whiteboard, it seems. So how do we show that? We have D of f so this, so basically this and this, I'm using the fact that and query complexity of f of XOR is essentially the same as query complexity of f. And I want to end with one open question, which I will write here. One letter, why not? Is what happens if you look at quantum models? So now in the quantum setting, for query complexity, it's known that D of f is at most poly in Q of f. And I guess it's very interesting to ask what happens if you also look at quantum query algorithms with OR queries or with and OR queries. Can we use similar techniques to try to show a polynomial relation here? I've thought about it for a while. I don't have answers. Yeah, I think I'll end here. Thanks.
The question, it would suffice to lower bound with this log number, this group. You tried that.
It would suffice to lose.
Suffice to lower bound your and one with this log number.
I have tried that. So maybe I can say another word about this. So the way you show that quantum is poly-related to deterministic or randomized in the classical in the regular setting is you have this, and then there's another measure that comes in between here, which is the approximate degree of it. And if you just plug it as it is, approximate degree of f can't be used as a lower bound for quantum and or quantum or complexity because and function has. So there should be a variation of approximate degree that is at least as large as block number is my point. So there should be an analog of approximate degree is at least square root log sensitivity. And I'm not sure what that analog is. I mean, it should be some sort of monomial measure or approximate L1 norm measure, but haven't been able to figure it out.
Well, if I think of other measures, you can look at size, so we can look at the UC size.
This I haven't thought about it. This is unambiguous certificate.
That's like a partition instead of.
Yeah, I don't know what happens with these.
Well, if you give a decision tree, you automatically get the application.
Yeah, right. So it's a different measure. But it makes sense to ask about size rather than.
I don't know how these relate. It would be known. I don't want to correct.
I have a question. So the n of f that you use here, so do you really need this to be a partition or a cover, or does it matter?
In what sense? I mean, how were you
So
thinking of?
the way you define it, so this S you want to define it to be a cover. But you want to cover. Now, in your proof, that in your theorem 1, do you actually get a cover or do you get a partition?
It's a good point. I need to think about it, but I think we get a cover. Like there's sort of two steps that go on. Like so let's see. So you get a bunch of certificates for different x's. I think for all we know, these might intersect. I don't know if we can guarantee a partition.
Any more questions? Okay, if not, let's thank Nikhil again.